Okay, so we're still continuing with 3.3.2 gas exchange, but this time we'll be looking at features of plants that limit water loss. So from the specification from AQA, structural and functional compromises between the opposing needs for efficient gas exchange and the limitation of water loss shown by xerophytic plants. So limiting water loss in plants, the learning objectives are: how do terrestrial plants balance the need for gas exchange and conserving water? How do plants adapt to living in areas where water loss from transpiration may exceed their water intake? What are xerophytic features? Limiting water loss in plants. Opposing needs. So plants have opposing needs of gas exchange and conserving water. That happens in any terrestrial organism, like insects also have a conflict between the fact that every time they open their spiracles, they're going to lose water through the spiracles, but they need to open them periodically for gas exchange. Likewise, plants, they open their stomata to allow carbon dioxide in, oxygen out, but every time they do that, water can be lost via evaporation through the stomata. And unfortunately, the features that are good for gas exchange are the same features that increase water loss. Terrestrial organisms limit water loss without compromising gas exchange. Insects reduce water loss by having a waterproof covering and a small surface to area to volume ratio. Plants also have a waterproof cuticle or covering, but they can't have too small a surface area to volume ratio because they need a large surface area to be able to capture light for photosynthesis and also for gas exchange. So how do plants limit water loss? So xerophytic plants, normal plants can obtain enough water to survive without many adaptations for reducing water loss, because they have a waterproof covering over parts of their leaves and they can close their stomata to be able to survive. However, plants that don't have a plentiful supply of water have to have other adaptations to limit water loss through transpiration, and these are known as xerophytes. So a cactus is an example of a xerophyte. And xerophytic plants are adapted to living in areas where water losses due to transpiration exceed the water uptake. Without these adaptations, these plants desiccate and die. Xerophytic plants have modifications to increase water uptake, to store water, and to reduce transpiration. The main way of surviving in an unfavourable water balance is to reduce the rate of water loss through transpiration. As most transpiration occurs through the leaves, it is these that show the most modifications. So some adaptations are as follows. Some can have a thicker waxy cuticle. Quite often these days they're asking you to say thicker waxy cuticle, or waterproof barrier, and about just less than 10% of transpiration can still occur even with a very thick waxy cuticle. So the thicker the cuticle, the less water can escape. Many evergreens such as holly have thick cuticles to reduce water loss in winter when the soil is frozen. Having this thick waterproof waxy cuticle also increases the diffusion distance for water to escape, and it provides a waterproof barrier. Rolling up of leaves. Stomata on the lower epidermis, and rolling of leaves protects the lower epidermis from the outside, like the wind. And it traps a region of still air which becomes saturated with water vapour. So therefore it reduces the water potential gradient. And because the water potential gradient is reduced, transpiration is also reduced. So marram grass, which lives in hot, windy conditions on the sandy seashore, they don't have much in the way of soil, so they can't get much water from their soil, and also because of the wind, that will take away a lot of the water vapour. So having these rolled leaves and trapping the water vapour will mean there's a layer of this humid air trapped in here, which reduces the water potential gradient from inside the plant, the air spaces, to the this trapped humid air here. Another adaptation is hairy leaves. So plants such as heather can have a thick layer of hairs on their leaves on the lower epidermis to trap a layer of moist air. Again, this reduces the water potential gradient, so less water is lost by transpiration. Next one, stomata in pits or grooves. That means they trap moist air next to the leaf and reduce the water potential gradient. Therefore, the rate of transpiration is reduced. Other things they can do is a reduced surface area to volume ratio of the leaves. This is not ideal because they obviously would then have to reduce the rate of photosynthesis. But if they live in extreme conditions where they can't get enough water, they can reduce the surface area to volume ratio of the leaves. Smaller surface area to volume ratio slows the rate of diffusion, and some examples are the small or circular leaves like pine needles rather than broad flat leaves. The reduction in surface area, though, must be balanced against the need for sufficient area for photosynthesis to meet the requirements of the plant. So, some features of xerophytes straight from a mark scheme from AQA. So, they have a thicker cuticle. They can have a thicker cuticle, so it increases the diffusion distance. It's got hair. They can have hairs on the leaves, which decreases the water potential gradient. It's got curled leaves, which can decrease the water potential gradient. Sunken stomata, which can decrease the water potential gradient. Basically, if in doubt, these three, just say what the feature is and that it decreases the water potential gradient. You can also say things like, so the hairs on the leaves reduce air movement, increase humidity. Curled leaves, reduced air movement, increased humidity. Sunken stomata, reduced air movement, increased humidity. But I would always say that most commonly in the mark schemes, it's hairs on leaves, decrease in water potential gradient. Curled leaves, decrease in water potential gradient. Sunken stomata, decrease in water potential gradient. I would also say, add to that and say which reduces the rate of transpiration. Just because mark schemes change every year, you never know, you might as well put more and definitely get the mark. Some math skills now, but before we do that, I'm just going to go over the layers of the leaf. So in the leaf cross section, you've got the waxy cuticle, which is a waterproof barrier, increases the diffusion distance for water to escape. The upper epidermis is a see-through layer which allows light to pass through. The palisade layer, they are the main photosynthetic cells, so they are packed full of chloroplasts for photosynthesis, to absorb light for photosynthesis, and they are cuboidal shaped so that they can stack nice and neatly in rows so you can get more of them so they can absorb more light. Then you've got the spongy layer, which is made of spongy mesophyll cells, but there's also air spaces. These air spaces are useful because it means that carbon dioxide can get the majority of the way to the palisade cells via diffusion in the gaseous phase, and diffusion in the gaseous phase is a lot quicker. So these air spaces help to increase the rate of diffusion. Then you've got the xylem, which carries water and ions, and phloem, which carries sugars like sucrose. On the lower epidermis, every so often you've got guard cells. The guard cells can open and control the stomata. The stomata are the little pores on the lower epidermis. You can sometimes find them on the upper epidermis, but they're mainly on the lower epidermis so that they are protected from the outside elements like wind, protected from evaporation from the sun, so less water loss. So here's what the stomata would look like. This must be a scanning electron micrograph because it has 3D and it's a surface. This one's more likely to be a electron micrograph because it's showing a section through the stomata. Through the stomata and through the guard cells. So the guard cells are either side, and then the stomata is this little pore in the middle. So these sausage shapes are the guard cells, and the middle is the pore. So just a bit of math skills to investigate the distribution of stomata and guard cells. So a simple method for doing this is paint the surface of the leaf with clear nail varnish, allow it to dry, peel off the nail varnish with forceps, place on a dry microscope slide and examine, record the distribution. So the density of stomata on a leaf is recorded per unit area, which is usually the number per square millimetre. And a microscope is calibrated so that its field of view is known. So a thing that they quite like to do is give you the diameter or the radius of the field of view, and then you have to find out the area of that. So in the illustration, the diameter of the field of view of the microscope is 0.4 millimeters. Its area can be calculated using the formula pi r squared. So remember that the radius is half of the diameter. So where pi is 3.14, the radius of the field of view. So if the diameter of the field of view is 0.4, the radius is half of that, 0.2, and then you just put pi times 0.2 times 0.2 or 0.2 squared. Make sure you use BODMAS for this. I would always do the 0.2 squared first and then times it by 3.14. So the answer is 0.13 millimeters squared is the area of the field of view. The number of stomata in the field of view is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you've got 12 stomata in 0.13 millimeters squared. But you usually want to know how many there are per 1 millimeter squared. So then you would just find out how many there are per meter squared. So you do 12 divided by 0.13 and you should get 92 stomata per millimeter squared. And then finding the surface area of a leaf. If you just wanted to find one surface, so like the upper surface of the leaf, you would count anything that is more than half a square. You don't count anything that's less than half a square, so you wouldn't count that. You wouldn't count that, you wouldn't count that. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 24 centimetres squared. So you'd lay your leaf on a piece of graph paper, draw around it, count anything that is more than half filled with the leaf, and then you add it together. Sometimes you'll have to times it by 2 if you want to find the total surface area of the leaf, because you've got, don't forget, you've got the upper epidermis and the lower epidermis. Okay, a sample exam question now. Use your knowledge of gas exchange in leaves to explain why plants grown in soil with very little water grow only slowly. It is because the stomata will close, which means less carbon dioxide could be taken up for photosynthesis. Ta-da!